Okay. Right. Good afternoon, everybody. I'm here from Linköping University, Sweden, and I'm going to be talking about the additive manufacturability of the nickel-based superalloy for LPPF process. So the trade-off here is, in the end, you will get the model that you just implement the composition of that random superalloy. It gives you the results of the printability of that alloy. So what is the nickel-based superalloy? This is the alloy system used at very high temperature. For example, the turbine blade, the creep property is one of the most used indicator for these materials. And the temperature for the hundreds of hours creep life at a certain load as a function of the year of development. Actually, the material's capacity in terms of operating temperatures increasing a lot. For example, from 700-ish to 1100-ish or even plus. But the one should also bear in mind that the revolution of the manufacturing way also gives you a very big improvement of each grade of alloy. And also you can name the grades of those alloys, which are well adapted for the specific manufacturing way. That means that for the additive manufacturing, a new composition is required. And from the physical methodology perspective, there are two major sources to provide the high temperature strengthening factor for these materials. The first one is named as the precipitation strengthening in the operating state. In the modern superalloy, it contains of around 60 to 70% of the gamma prime phase, which is an intermetallic phase, L12 phase. And another way is by solutioning strengthening. This advanced superalloy doped a lot more than 10 or even more different alloying system. As one of the lectures this morning said, the nickel is a very good solvent for adding elements like, for example, cobalt, chromium, rhenium, and the tungsten. And those refractory elements engaged in the gamma channel improve the strength at those positions. And from the community of welding of the nickel-based superalloy, in the textbook, people in the industry refer to this diagram to put the aluminum and the titanium amount in weight percent to judge a superalloy's weldability. The reason is if one alloy sits at the top right corner, those alloys are considered as non-weldable because of the high strain edge cracking susceptibility. But I hope you still remember for the high gamma prime amount of superalloy is highly demanded, but unfortunately, both aluminum, the titanium, are the primary gamma prime formers. So there's a knowledge gap. What is the chemical composition to the additive manufacturing or the printability of this alloy? That is a big question mark. From the multi-scale microstructure in the LPPF superalloy, there are quite different scales to look into the microstructure. Under the optical microscope, you find those multiple boundaries around 10 to 100 micron, depends on the beam diameter and other parameters. And down to scanning electron microscope, you found those sonification structures. And under the TEM scale, actually at those cellular boundaries or the region at the lost sonified region, they are composed with very high density of dislocation. And also this region carries the segregation information, and it can be confirmed by the atom probe tomography. For example, in this case, the two-dimensional element contouring map shows the titanium is enriched in this so-called interdendritic region. And the insights from the cracking mechanisms from welding, there are four well-defined mechanisms. The first two, simplification equation cracking, which occur during the process. And of course, there are third and fourth, which is affinity deep and strain edge cracking, which requires the involvement of the precipitation happen. But in a superalloy with a well-aged condition, more than 60% precipitate. In the as-built condition, from the atom probe tomography, aluminum, nickel, and chromium for the gamma prime former, gamma former, and the metric element, they are distributed quite randomly in the volume, and they follow the serratic distribution. So we can consider in attribute condition, there's a supersaturated solution. Then I want to say something about the roadmap towards so-called additive manufacturability, the HRDR model. And in the attribute superalloy, we have the DC and ID. DC is dendrite core, ID is interdendritic region. I consider them as a composite-like materials, so they share different composition. And from the literature or your experience, you will find the ID is a vulnerable place. That means the microcrack always attacks the regions like the ID. Then the road can be given like this for given composition by using the knowledge of microsegregation. I separate this material into two regions, ID and DC. Then I compare two indexes. The first one is heat resistant, in short HR. Another is deformation resistant, in short DER. Think about this question. If one alloy has both stronger DR and HR than the DC, that alloy is supposed to have better resistance to the cracking during the AM process. Then let's try to formulate this model. First step, of course, is to assign the composition to DC and the ID. As the previous the presentation talked a lot about the segregation profile, I also used this. For example, the segregation profile normally looks like this. It's a curving, it's a gradient, it's not a stepwise. But I did a shortcut which made the assumption. That is for the attribute microstructure, 70% of the region belongs to the DC and 30% belongs to the ID. It's approximation. Then I used level rule-like assumptions like this. So the area of the nominal composition equals to the area of the CD times the fraction, of course, plus CID times the fraction. Then I can quickly get this composition for these two regions based on the, of course, the nominal composition and of course another parameter I will introduce. There are inference from the rapid cooling and solidification, and we went through very detailed last talk. The classic shell and the solid trapping at the very wild solidification rate at -4 meter per second, which is equivalent to those solidification rate to the solidification, directional solidification for producing single crystal superalloy, and also solidification rate at 1.0 meter per second. That is equivalent to the LPBF process. There are some features. First of all, the profile looks different, and second, the absolute value of the partitioning coefficient are different. And here I did this. I have 70% of DC. I integral this region and to consider it as a composition for DC. Then I put this CDC as a function of the nominal composition for each element, and did a simple linear regression, giving me a so-called partitioning coefficient in this case. The only reason is that this K value can quickly separate the DC and ID value in this way. And of course, there are some other formulating of the HR and DR indices. The DR deformation resistant, I naturally think about the strengths. There are a couple of physics-based model. One of the model can be written like this: yield stress equals pure stress plus solid solution, grain boundary, gamma prime, and dislocation. Here, I want to use subtraction. I use ID minus DC, so I can cancel out the same matrix, so it's disappeared. And there's no gamma prime, I assumed, and I think some of you may agree this also. Then this difference of the delta sigma can be rewritten like this difference between the solid solution strengthening. And this, the last two parts, actually they are highly dependent on the printing parameter. So I put this as a C. If you have same or similar printing parameters, then I can consider those as a constant value. Then it's very easy to read in a compositional average form. And for the heat resistant, I considered the solidus temperature and did the same tricks, delta T, solidus temperature difference, equals to the ID solidus temperature minus the DC solidus temperature. And also from this thermocap binary phase diagram, you can see that by adding certain amount of the alloying elements, actually the solidus line is decreasing in a semi-linear regression. So I put just the average, compositional average to quickly calculate the solidus temperature of each locations. Okay, then we look into this so-called additive manufacturability diagram. It was visualized for this model and from the experimental data as much as I can find. On the y-axis, I have the heat resistant, and on the x-axis, I have the deformation resistant. And I hope you still remember those alloy at the top right corner. They have both higher heat and deformation resistant. They are okay. And it turns out, yes, they are crack-free from the literature data. And those alloy, which has a not very good resistant ID region, so they are cracked. So it follows quite well with the theory and this experimental data. And also, this is a pure chemical composition model, and I try to define boundaries to separate the alloy into this region and another region. This region is printable, another region is non-printable, and it shows excellent predictability. And also, because it's fully based on the chemical composition, the inference of each element can be reviewed, and the most importantly, it gives you the numerical criteria that can be used for the following alloy development process, etc. And the inference of the gamma prime and minor elements on this additive manufacturability, I put this diagram with different colors and bubble size. You can see the size of bubble indicates the gamma prime volume fraction at the equilibrium state. Actually, for example, the EXPM from Carpenter, they are kind of a very high gamma prime amount. They can be printed in a very good condition, crack-free condition. And the CM247 still have very high amount of gamma prime, but they cannot. That means there are a very large dependency of the gamma prime amount on this printability map. But instead, you can see this sum of minor and hafnium, boron, and zirconium. We were talking about those minor elements. It shows a strong indication for the printability. And also I try to involve more alloy, not only the nickel-based, for example, Professor Pollock's cobalt nickel alloy sits here at a relatively high amount of gamma prime, and it's printable, we know from this morning. Okay, yeah, this is a model. It's open access. You can just take the stuff, and it's very easy to calculate. I'm a very bad program. I just use the Excel worksheet. That's the easiest way for me. What I did, this is I put the composition of alloy element. Then you will see this mark, your demo alloy, on this map. Then that, I think it can help you, can assist you to find out a suitable window for each element. It includes almost all the alloy elements, and hafnium, carbon, boron, zirconium, silicon. Those minor elements are also appreciated. All right, thank you very much. I think